Lesson 5-5 functions, and in this lesson you'll determine whether a given relation is a function and to find the value of a function for a given element of the domain. Why is it important? Because you can use functions to solve problems involving accounting, earth, science, and health. Let's take a look at this example in air travel. During certain times of the year, airlines offer lower rates to fly selected cities. The advertisement below shows discount ticket fares. The mileage between the cities is also listed for those people who are enrolled in frequent flyer programs. Let's take a look at this chart right here, this table. From Atlanta to New York, the regular fare is $89. The discounted fare is $79, and it's 892 miles apart. Okay, Baltimore to Houston is $149. Discount fare is $129. 1,454 is the mileage. Okay, and so on and so forth. Los Angeles to San Antonio, the very bottom, regular fare $139. Discounted fare is $129. 1,277, okay, is the mileage. Okay, so what we want to find out is that suppose we let R, okay, we let R represent the regular fare, and D represent the discount fare, and M represent the mileage. The relations whose ordered pairs are the form of RD, okay, which means the regular fare and discount fare is graphed below on the left. So this is the graph of that one, okay, where R is your regular fare, okay, and related to the discount fare, okay. The relation whose ordered pairs in the form of MD, where M is the mileage and D is the discounted fare, is graphed on the right, okay. Okay, and if you notice that the graph on the left, when R equals 109, there is more than one value of D, okay, 79 and 99. So where this is 109, when R is 109, which is right around here, I would imagine. Okay. Okay, when R equals 109, is it here? Yes. Okay. There's more than one value, 79 and 99. Okay. And if that's not too clear on the graph, look at this one when R equals 99. Okay, R equals 99. Is it 99? Yes, it is. Sorry, 109. So when R equals 109 right here, okay, your discount fare is, okay, 79 and 99. So you have your 79, okay, and you also have 99 right here, okay. Sorry, right there. So 109 and 99, 109 and 79, these two, okay. So it also shows in this graph, which is around these two, right there, okay. All right, now we found it, okay. However, in the other graph, there is exactly one value of D for each value of M, okay. So if you look at this other graph, you will notice that for every value of D, okay, there's always one value of M, okay. Relations with this characteristic are called functions, okay. So let's define what a function is after looking for all those fares, okay. Oops, not there, it's down there, down here, okay. So definition of a function, let me put that up first, okay, right there, going down again. Definition of a function is a relation in which each element of the domain is paired with exactly one element of the range, and this is a good example of what a function is, because each element of the domain right here, okay, and your x-axis is paired with exactly one element of the range. Unlike in this graph right over here on the left, okay, you have two elements, okay, of the range is paired with one element of the domain. Okay, now let's take a look at how we can apply this, determine whether each relation is a function, and explain your answer. Okay, look at it, the first one. You have ordered pairs 2, 3, 3, 0, 5, 2, -1, -2, 4, and 1. Okay, if you look at it closely, okay, each element of the domain is paired with exactly one element of the range. This relation is considered to be a function. Okay, let's take a look at letter B. Okay, in letter B, you have a relation that has been mapped out. This is the mapping of a relation. Okay, so this mapping also represents a function, since for each element of the domain there is only one corresponding element in the range. Okay, now if you notice, -3, -8 points to the same number 10, and it does not matter if two elements of the domain are paired with the same element in the range. What matters is that for each element of the domain, there is only one corresponding element in the range. Okay, again, what it's saying here is that the domain can point to the same element in the range, okay, for as long as they are different domains. -3 and -8 is paired with the range of 10. But look at letter C. Okay, in letter C, okay, this is not a relation. This relation is not a function. Why? Because look at the element 5. Okay, if you look at the element 5 right here, it is paired with both 2 and 3. So that means this domain is paired with two ranges, 2 and 3. So it does not correspond to our definition of the domain, which says that each element of the domain is paired with exactly one element of the range, and that's the reason why example C is not a function. Okay, I hope that is clear. If not, rewind me and listen to it again, because this will become important later on. Okay, so there are several, if I can click it, okay, or is it on the next page? I think it's on the next page. There are several ways to determine whether an equation represents a function. Look at the example number 2, determine whether x minus 4y is a function. So first method, obviously we can use a table for this one, okay, and then again what we did in the last lesson, to make a table you need to solve for y first. That means you need to isolate y, okay, therefore we copy the problem first, okay, x minus 4y equals 12, and then we subtract x to both sides. We end up with -x plus 12, and then we divide both sides by -4, I'm sorry, so y equals 1/4 x minus 3. Now that we have solved for y, we can create our table, okay, and this is the table that we can create. So if we let the domain be -8, -4, -2, 0, 2, 4, and 8, okay, and substitute these values to x right here, okay, what's going to happen is that after we substitute the x to that x, we find the values of y, corresponding values for y is -5, -4, -3.5, -3, -2.5, -2, and 1. Okay, now look at those values, okay, and look very closely if each element of the domain is paired with exactly one element of the range, okay, and we know for a fact that it appears that way. There's only one value for y that will satisfy the equation, therefore, okay, x minus 4y is considered to be a function. The next method that we are going to look at is what we call, okay, the vertical line method. Okay. So how do we do that? Since the equation is in the form of ax plus by equals c, the graph of the equation will be a line, such as that one. Graph the ordered pairs from method 1 and connect them with a line, and we just did that right there. Okay. Now place your pencil at the left of the graph to represent a vertical line, and slowly move the pencil to the right across the graph. So what you do is you get your pencil and slowly move it to the right across the graph. Now what do you notice here? Okay, for each value of x, okay, this vertical line, the black line that I have, passes through no more than 1 point on the graph. Thus the line represents a function. So every time I move this vertical line back and forth on that particular straight line, okay, if you notice, it will only intersect that particular line at 1 point. So that intersects at that point. Okay, if I move it again and I move it to this point, it intersects that line at 1 point. If it only intersects your line at 1 point, okay, using the vertical line method, then this is considered to be a function. Okay, so using a pencil to see if a graph represents a function is one way to perform the vertical line test. Okay, so let's define the vertical line test. Okay, if any vertical line passes through no more than 1 point of the graph of a relation, then the relation is considered to be a function. Let's take a look at example number 3, and using the vertical line test, let's find out if A, B, and or C are functions or not. Okay, so this is my vertical line, and if you notice, as I pass through this graph right here, it intersects my vertical line at 2 points. So since it intersects my vertical line at 2 points, this is not a function. Okay, so we can cross that out, not a function. Okay, and we move on to B, and if you notice, okay, every single time I move it to the right, my vertical line will intersect that line at exactly 1 point every single time. Okay, so therefore this is a function. We give a check to that as a function. And finally, let's look at letter C. Okay, as I move my vertical line across, okay, it will intersect my vertical line and the graph at 2 points. So therefore this is not a function. So let's summarize what we just did. Graph B is the only relation to pass the vertical line test. Thus it is the only function. With the graphs A and C, a vertical line intersects the graph in more than 1 point. Okay, thus they are not functions. Okay, let's take a look at this one. We also know that equations are the functions. Sorry, equations that are functions can be written in the form called functional notation. Okay, for example, let's consider the equation y equals 3x minus 7. So the equation is written as y equals 3x minus 7. The functional notation of 3x is written this way, where you read it, this particular term here or expression is read as f of x. So the symbol f parentheses x is read as f of x. Okay? So in a function x represents the elements of the domain, and f of x represents the elements of the range. Okay, again, in a function, x represents the elements of the domain, and f of x represents the elements of the range. So basically, f of x is your y. Okay, suppose you want to find the value in the range that corresponds to the element 4 in the domain. So this is written as f of 4, and is of course read as f of 4. The value of f of 4 is found by substituting 4 in x of the equation. So simply put, if you want to find the value in the range which corresponds to element 4 of the domain, okay, you create an equation using functional notation. So f of 4 equals 3 times 4 minus 7. Because the equation is 3x minus 7, you simply substitute 4 to x, okay, and f of 4 to y. So you now have f of 4 equals 3 times 4 minus 7, or 5. Okay, so for if the x is 4 in this case, what it's saying that if x is equal to 4, why is that an x? I don't know why that's an x. My finger are doing stuff I'm not commanding it to. So if x is equal to 4, the domain would be equal to 5. So your ordered pair, sorry, the range would be equal to 5. So you have an ordered pair of 4 and 5 there. Okay, let's take a look at example number 4. F of x equals 2x minus 9. Find each value. Okay, so what is f of 6? We simply substitute 6 to x. You end up with 2x minus 2 times 6 minus 9, 12 minus 9. So f of 6 is equal to 3. What is f of negative 2? We substitute negative 2 to x. 2 times negative 2 equals minus 9. Okay, that becomes negative 4 minus 9, or negative 13. So f of negative 2 is negative 13. And let's take it one step further using an algebraic expression. Okay, what is f of k plus 1? We substitute k plus 1 to x. So this becomes now 2 times k plus 1 minus 9. Using the distributive property, this becomes 2k plus 2 minus 9. Simplifying it further, it becomes 2k minus 7. Okay, so the functions we have studied thus far have been linear functions. Many functions are not linear. I showed you some of the graphs which are not linear. However, you can find values of functions in the same way. Okay, so this is not a linear function. Well, actually, this is a linear function, but not as it is a function. Let me correct myself. It is a function. Okay, it is not a linear function. Okay, and let's see how this works in example number 5. If h of z is equal to z squared plus minus 4z plus 9, find each value. What is h of negative 3? We simply substitute negative 3 to z on those, and we end up with negative 3 squared minus 4 times negative 3 plus 9. Simplifying that, we end up with 9 plus 12 plus 9, or 30. Okay, what is h of 5c? Again, we substitute 5c to z, and we end up with 5c squared minus 4 times 5c plus 9. It is also important to note that you need to put 5c in parentheses, okay, but because 5c squared is not equal to 5c squared. Okay, 5c squared in parentheses is 25c squared, and 5c squared not in parentheses is simply 5c squared. And so you can see these two are not equal. Okay, continuing that, you now have 25c squared, which I showed you, minus 20c, 4 times negative 5 times 5, negative 4 times 5 is negative 20c plus 9. Okay, and that would be h of 5c. Okay, and finally, let's take a look at c before we go to the last example. And in C, it's asking 5 times, okay, h of c. Okay, so we simply multiply the whole equation, okay, by 5 and substitute the value of c to z. So you now have 5 times c squared minus 4c plus 9. Okay, simplify what's inside the parentheses, and then distribute 5c squared minus 4 times 4c times 5 plus 5 times 9 will give us 5c squared minus 20c plus 45. Okay, so that would be 5 times h of c. Another way of doing this is, so you won't get confused that much, is get h of c first. So if you want to get h of c is no more than c squared minus 4c plus 9, right? And then after you get h of c, you simply multiply that by 5. So now you get 5 times h of c will be equal to 5 times c squared minus 4c plus 9. And that's where we pick it up from there. Okay, and finally there. Okay, so if you're getting confused, break down the problem. Okay, so it'll be easier for you to solve. And finally, the last example. Functions are often used in real-life problems. Okay, the normal systolic blood pressure, S, is a function of the age of the individual. Okay, so if you look at this sentence right here, the first sentence, you know right away what is the independent and what is the dependent variable by reading the sentence. Again, we read it. The normal systolic pressure, S, is a function of the age of the individual, meaning that S is dependent on age. You can actually restate this as the normal systolic blood pressure, S, is dependent on the age of the individual. Okay, so S is your dependent variable, A is your independent variable in this example. Okay, so that is a person's normal blood pressure depends on how old the person is. To determine the normal systolic blood pressure of an individual, you can use the equation S equals 0.5A plus 110, where A represents age in years. Okay, so this is a good way to find out the blood pressure of your parents if they are willing to share it with you, and this will tell you if their blood pressure is normal or not. Okay, you can also use this on yourself. So first, write an equation in functional notation, and then letter B, find S of 10, S of 30, S of 50, and S of 70. That means the age is 30 years old, 50 years old, 70 years old, and 10 years old. And then it's asking you to graph the function, name the independent and dependent quantities. So I just did that for you. And letter D, use the graph of the function to estimate whether blood pressure increases or decreases with age. Then estimate the blood pressure of an 80-year-old person. So in letter D, we are going to predict after creating the graph. So let's look at letter A. S of A represents a function, so our functional notation for that equation would be S of A is equal to 0.5A plus 110. Easy enough. And then we make a table with 10, 30, 50, and 70 as values of A. So that's your A, 10, 50, 70, 50, and 70. And 0.5A plus 110 is the expression or the equation, okay, in this case. And we simply substitute the value of 10 for this for A, and S of 10 is equal to, okay, 115. That is your S of A, okay, or your dependent variable. S of 30, substituting that, will give you 125. S of 50 will give you 135, and S of 70 will give you 145. So you have your ordered pairs now, A and S of A. Remember, S of A is also your dependent variable or your Y coordinate. So you have 10 and 115, 30 and 125, 150 and 135, and 70 and 145. Okay? So we will use these ordered pairs from the table to graph the function. Okay, again, age, that is the independent quantity, and systolic blood pressure is the dependent quantity. And this is how our graph would look like. It is a linear function. Okay, so that's our graph. Now that we, after we've connected the 4 points with a line, we can proceed with letter D. We can now predict. So the graph indicates that as you age, your blood pressure is expected to rise. So an 80-year-old person would expect to have a systolic pressure of around 150. Why is that? Because if you extend that graph, and you look at 80 years old, which is this one, okay, and if I go up, okay, from 80 going to that line right here, you notice that it hits, okay, 150, okay. So an 80-year-old person would expect to have a systolic pressure of about 150, okay, which this can actually give us a lot more uh, information. For example, if you are asked to, let's put this in the color of red, okay, if you're asked to find the systolic blood pressure, let's say of a person who's age 40, all you need to do is go to 40 and then go there. So at 40 years old, your systolic blood pressure should be around 130, okay. And if you're 60, okay, if you have a 60-year-old, the systolic blood pressure is around 140. And that's how you determine systolic blood pressure, by looking at a linear function. And that's it, boys and girls. Thank you for watching.